propellers can also have a significant effect on the trim and stability of an aircraft. And so let's look at this. We're going to look at a propeller here, and look at it from the front, and we'll look at it from the top. So this is a top view looking down, and this is a side view of that propeller. So here's our the nose. So it's moving in this direction, and we'll say that it's moving in a right-handed rotation about its axis, and so we have the rotation in this direction here. And actually I want to draw these blades like this. Okay, so there's our top view and our side view of this propeller. And so it's got a this is a right-handed propeller. If you put your thumb in the direction that it's moving, which you can see over here, then it's rotating in the direction that our fingers curl. And so this propeller, the front view of it is actually coming out of the page towards us. Okay, so let's put let's look at the forces on this, the lift, and so I'm going to call them lift and drag forces on the blades of this propeller as it moves around. As it moves around here. These aren't exactly the lift and drag, but these are basically the in-plane forces and out-of-plane forces, okay? So let's look at drag first. So drag is this in-plane force, and as it rotates around, the drag, so it's moving in a counterclockwise direction here, and so drag is going to act opposite to that direction. So actually let's put drag in red here. So that's our drag, and it's going to be the same on the blades all the way around if we don't have any angle of attack on the propeller. Okay, now let's put an angle of attack on this propeller. So let's say that now the velocity that is seen is coming in at an angle. So we'll call this angle alpha, alpha of the prop. So this is the local angle that we're seeing relative to the axis of the propeller. Okay, so here's the axis of the propeller. And let's say we have some angle of attack. Well, what happens over here is that because this blade that's going down, well, first I should draw maybe, we have now two components of velocity that this propeller is seeing. We have a normal component here that I've drawn, and we also have the axial component. So some of the flow is going directly along the axis of the propeller, but now we have a new component that's also going normal to the propeller. So I'm going to draw that here, and that's across the entire propeller. We have this normal component of velocity that it's now seeing. So because of that normal component of velocity, the velocity that this blade sees is actually larger as it's coming around here. This blade is going to see a larger velocity because it not only has its angular rate velocity along here, but it's also adding this component to it. Okay, so it's seeing a larger velocity than it did with the red arrows, where the free stream velocity was right along the axis of the aircraft. So we have a larger velocity, and that means our drag increases. Remember, drag goes up proportional to your dynamic pressure squared, or to your dynamic pressure, which is 1/2 rho v squared, right? So we have a larger dynamic pressure over here, so our drag is going to increase. So let's draw that here in blue. So we're going to have a larger drag than we used to. And let's look at the drag on this blade. So actually, as this rotates around, it's now moving in the same direction as this velocity. So the fact that we have some velocity in this direction actually decreases the drag or the dynamic pressure that the blade sees on that side. And so because we're decreasing dynamic pressure, we also decrease the drag. So there's just a little tiny drag vector there that's smaller than than the red drag vector. Okay, so the net force in drag on this side of the propeller is going to be a net force in the upward direction that is new due to the angle of attack. And if we look at the drag on this side, it actually now has a net force as well in that direction. So both sides of this propeller create a net force upward from the force that it used to see, which was 0 if the free stream velocity were aligned with this axis. Okay, I hope that makes sense. So what this ends up doing is we create this normal force, and I'm just going to put it right here. We call this N sub P. This is the normal force of the propeller. And it turns out that normal force acts in the direction of the normal velocity that this propeller sees. So if it has some free stream velocity that's coming in from the bottom of the propeller, then it's going to or create this normal force in the upward direction of the propeller. I should put an arrow here. So it's going to be upward. And the same thing is going to apply once we get into lateral. You'll see what if we have some side slip. So what if the flow is coming in from the side over here? Well, then we'll get a net force in that same direction. Okay, so whatever direction the flow is coming in from, we get a net force in that direction due to a difference in drag on the blades as they rotate around. Okay, so now let's look at lift. We can go through the same analysis, and what we'll find, let me maybe put this in a different color. So the lift now will also be actually greater on this side of the aircraft due to the increase in dynamic pressure, and the lift on this side of the aircraft though will actually be less due to the dynamic pressure. So from this perspective, it's hard to see, but let's look at the top-down view that I drew up here. So if we have an increase, so originally, let's draw in red. Originally we had the same amount of lift on both sides of the propellers coming out, in the direction that we're creating thrust. But due to this change in lift on the one side, we're actually going to have an increase in lift on one side and a decrease in lift on the other side. Well, that actually creates a net yawing moment. So as the angle of attack changes on this, it's going to create a yawing moment due to the aerodynamics of this propeller. Okay, so I just wanted to talk through this as kind of an introduction here to see where these forces and moments come from for the propeller. Now this section, we're only looking at longitudinal forces and moments, and so we're only going to look at the effects due to angle of attack and the resulting normal force that comes from that. The resulting yawing moment that comes due to our difference in lift will be discussed later when we get into the lateral effects of a propeller. So let's just look at this from a longitudinal stance, and we'll go back to our white here. So let's say that we have our center of gravity and a fuselage reference line that is aligned with our thrust vector, and this is where our propeller is, right here. And in general, we're going to say that this is L sub P, that's the distance after the CG to that propeller, and H sub P is the vertical offset of that propeller. And then now we're not going to only include the thrust, which is obviously a big component to our pitching moment, obviously if we have some vertical offset, but we're also going to include this normal force, that's N sub P, the normal force on the propeller that's a function of the angle of attack that the propeller is seeing. Okay, so now we can look at the pitching moment about the center of gravity. The pitching moment about the center of gravity due to the propeller is equal to the dimensional moment about the center of gravity to the propeller divided by 1/2 rho v infinity squared SW c bar W. That's the way that we've non-dimensionalized the global pitching moment. So we'll take the pitching moment from the propeller and non-dimensionalize it the same way. And let's just write that out. So the pitching moment from the propeller, so what we want to do is figure out the pitching moment about the center of gravity due to the propeller here. And that is equal to, so we have the height of the propeller multiplied by the thrust, and that will give us, if both of those are positive, so H sub P, and then thrust, and I'm going to non-dimensionalize those different ways. If both of those are positive, it gives us a negative pitching moment. So that's where the negative out front comes from. And then we're going to non-dimensionalize this by 1/2 rho v infinity squared S sub W. And I'm going to put the C bar W underneath the height because those are both a length, okay? And then we do the same thing. The pitching moment about the center of gravity due to the normal force is the normal force times this distance here. And if both of those are positive, again, we get a negative pitching moment. So we're going to get L sub P over C bar wing times that force N sub P over 1/2 rho v infinity squared SW. So again, we're non-dimensionalizing by the C bar. Really, this is the dynamic pressure, an area, and a length. And I've just split those up differently here. So I've got the dynamic pressure and area here because this is a force. I put the length over here because that's a length. Same thing here, length. And then this is a force and that's a force, okay? Now, for our simplified analysis, we're going to take this, we're going to simplify this a little bit. This particular component, we're going to say is for our analysis here, if we have just a single propeller, that's going to be equal to the drag. This is the drag coefficient, actually. Thrust divided by 1/2 rho v infinity squared SW. We're going to say it is about equal to the drag coefficient. Now, you could do a ratio that. You could say it's only 1/4 of the drag coefficient if you have 4 propellers, or 1/2 of the drag if you have 2 propellers, and each of the propellers are carrying the same load. And you don't even need to make this approximation if you want to carry it through, but we're just going to make that approximation. It will simplify this just a little bit, okay? So now let's look at the normal, this N sub P term here. It turns out that N sub P is directly proportional to angle of attack, okay? So if our angle of attack is 0, then N sub P is 0, and then we're going to assume that it's linear, that it increases linearly with angle of attack. So we can non-dimensionalize that. We're going to divide that by, the way that we usually do this for propellers is a little different than what we do on a traditional aircraft. So when we non-dimensionalize propeller coefficients, we usually use this, which is rho times omega over 2 pi squared times the diameter of the propeller to the 4th. Okay, so that's how that's usually non-dimensionalized, and then we would call this a coefficient, a normal coefficient on the of the propeller. So omega is the rotation rate of the propeller, and d sub p is the diameter of the propeller, and then rho is still the density of the fluid. So we're going to assume that Cn of P is can be expressed as Cn P comma alpha times alpha P. Okay, so that's that we're just going to assume that it's linear with angle of attack of the propeller, and that if the angle of attack of the propeller is 0, then it's also 0. That normal coefficient is 0. So let's plug all of this now back into this main equation here. So let's come down here. We're going to have minus H sub P over C bar wing times the drag coefficient minus, and I'm going to rearrange the stuff just a little bit because we've got this stuff here, and instead of this NP, I'm actually going to substitute in this non-dimensionalized this information here multiplied by our coefficient that we would have from the propeller. Okay, so we'll multiply these two together, substitute that in for NP, and what we'll get is minus LP over C bar W. That's what we had out front. And then we've got, once we do all that, we'll have rho omega over 2 pi squared dp to the fourth divided by 1/2 rho v infinity squared SW. And then we have the CNP alpha times alpha p there, okay? So this is our CM due to the propeller. Okay, so a couple more steps we want to take. One of those is the introduction of something called an advance ratio. So an advance ratio is usually given the symbol J, and it's a ratio of the velocity or the forward velocity of a propeller to the angular rate or the angular velocity of a propeller. And so that's defined as 2 pi v infinity over omega times the diameter of the propeller. So we usually like to look at these things in terms of advance ratio. All this stuff in here we're going to rewrite in terms of advance ratio. Another thing that we want to look at is the angle of attack of the propeller. And that is going to be equal to our free stream angle of attack. If we've aligned, so remember we've aligned this fuselage reference line with the direction of thrust. That's not a hard requirement. Actually, we're going to include a term here that will relax that a little bit. So we're going to have our free stream angle plus a mounting angle alpha naught p if we wanted to mount that propeller at a different angle to that fuselage reference line, and then we'd have minus epsilon dp. That's the downwash at the propeller. So what we're trying to do here is include the downwash that propeller might be seeing due to its presence, due to the fact that it's probably close to a wing. So if it's behind the wing, then we're going to get the positive downwash like we do with, or it'll be at a lower angle of attack like we do on the horizontal stabilizer. A lot of times, actually, propellers are up in front of the wing, and so we'll get upwash there. But we don't want to neglect the fact that it's probably near a wing, and we need to account for the upwash or downwash that would be coming from that wing. And we would estimate that upwash or downwash the same way that we would estimate it for the horizontal. We've talked about a way to estimate it there. You can use higher fidelity CFD or panel codes or whatever to estimate it to higher accuracy. But we do have a way to just estimate what that downwash would be as a function of where that propeller is located relative to the wing. Okay, so let's plug all of this in, and I'm going to do one other thing here at the same time. So we're going to plug this advance ratio in here. We're gonna plug this in there, and we're going to split up. We're going to say that Cm of the propeller can be written as some Cm naught of the propeller plus Cm alpha of the propeller times alpha. The reason we like to split this up is because this term here affects our pitch stability derivative on the entire aircraft. So we can take that term and just add it directly into our pitch stability derivative to see how the propeller is going to affect the pitch stability of the aircraft. And then, of course, we actually take both of these terms. Maybe I'll write this out here. This affects our pitch stability, and then both of these terms actually affect trim. So we would add both of them into our trim equation to trim out the aircraft. So I'm just going to write it in these terms here. So Cm naught of the propeller. Once we've plugged in this J for some of the terms in here, and then plugged in this definition of alpha p. Then that is equal to minus HP over C bar wing times CD, so that's our drag coefficient, minus, and now this is going to look a little different because we're putting this in terms of advance ratio, but we've got 2 diameter of the propeller squared times L sub P over SW C bar wing advance ratio squared times Cn P alpha times, now this first term is everything that is not directly proportional to our global alpha. And so when we plug this in here, we get these two terms here that are not related to the global angle of attack. So we've got alpha naught P minus epsilon dP. And actually, this epsilon dP, I forgot to add this in, epsilon dP equals epsilon dP naught plus epsilon dP alpha times alpha, where this is the downwash at 0 angle of attack, 0 global alpha, and then this is our change in that downwash with respect to alpha. So this is actually epsilon dP naught right there. Okay, so that's the pitching moment when alpha is equal to 0. When our global angle of attack is 0, this is the pitching moment on the aircraft. But then we also have this change in pitching moment with respect to alpha, the Cm alpha of the propeller. And it's the way we get that is just taking the derivative of this equation with respect to alpha. And that gives us a minus 2 dP squared LP over SW C bar wing times the advance ratio squared times CN P alpha times 1 minus epsilon dP alpha. Okay, so this is the final form, or at least for our discussion purposes here. This is a nice approximation for estimating the effects of the propeller on the pitch, trim, and stability. And one thing we can see here is that if LP is positive, then we're going to get a negative. So if LP is positive, then we're going to get that our propeller is stabilizing, okay? Because this gives us a net negative term, and so if this is positive, everything else in here is positive, and so we've got this minus out front, and so that gives us a net negative Cm alpha, which is good. We want well, I guess I shouldn't say it's good. It depends on the aircraft that you're designing, but that would add to our pitch stability. So if the propeller is behind the center of gravity, so our CG is here and the propeller is behind, then that is a stabilizing component. It will actually add to the pitch stability of the aircraft. If the propeller is in front, so if LP is negative, so if this guy were negative, then we'd get a positive pitch stability derivative term here due to the propeller. And so that's a destabilizing effect. And so and on a pusher aircraft means that the propeller sits at the back and pushes it along. And so that's a stabilizing configuration where the propeller is actually adding to the stability of that aircraft. On a tractor aircraft, that's where the propeller sits out front, in front of the center of gravity. That produces a destabilizing effect.